Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the current flow mechanism when the PN junction is forwardly biased. Let's start. By the time you finish this lesson, you will learn the effect of the forward biasing on the depletion region width, the concentration of minority charge carriers under forward biasing, and the current flow mechanism under the forward biasing. In the previous lecture, I discussed the equilibrium built-in voltage of a PN junction. In this lecture, I'm going to discuss the forward biasing of a PN junction. There's only two ways you can bias or drive a PN junction. The first one is the forward biasing. In this biasing, the positive terminal of the external voltage source is connected to the P semiconductor and the negative terminal of the voltage source to the N semiconductor. The second biasing is the reverse biasing. In this case, the external voltage source is connected reversely to the PN junction, the positive terminal to the N semiconductor and the negative terminal to the P semiconductor. In this lecture, I won't touch on the reverse biasing of a PN junction, and I only focus on the forward biasing. The next lecture will be about the reverse biasing. To connect the external voltage source to the PN junction, I need to add two metallic contacts, each on one side of the PN junction. Hereafter, I show the voltage level or the electrical potential of the external voltage source by V sub D. If V sub D is 0, the PN junction is in the equilibrium state and nothing new takes place. However, if I increase Vd a little bit, an electrical field between the two metallic contacts forms, where its direction is opposite to the direction of the depletion region electrical field. As a result of this externally forced electrical field, the holes in the P semiconductor and free electrons in the N semiconductor are pushed toward the depletion region. These pushed holes and electrons penetrate into the depletion region, and they compensate some of the ionized acceptor and donor dopants. As a result, the width of the depletion region decreases, and this makes the diffusion process for holes and free electrons easier. Let's take a look at the concentration of minority charge carriers for this abrupt PN junction across the device length. When there is no forward biasing, the minority charge carrier concentrations on both sides of the PN junction are flat all across the device. And of course, the depletion region is empty of any mobile charge carriers. In equilibrium, NP0 represents the concentration of free electrons as the minority charge carriers in the P semiconductor, and PN0 represents the concentration of holes as the minority charge carriers in the N semiconductor. NP0 equals Ni squared over N sub A, and PN0 equals Ni squared over N sub D. As I said, when Vd is greater than 0 volts, the depletion region's width reduces, and now the diffusion process gets stronger. This means that there are now more holes to diffuse into the N semiconductor from the P semiconductor, and more free electrons to diffuse into the P semiconductor from the N semiconductor. As a result of this magnified diffusion process, the density of holes in the N semiconductor near the edge of the depletion region significantly increases, and also the density of free electrons in the P semiconductor near the edge of the depletion region significantly increases. At the edge of the depletion region on the P side, the concentration of free electrons in P star equals NP0 times e to the power of QVD over KT. At the border of the depletion region on the N side, the concentration of holes Pn star equals Pn0 times e to the power of QVD over KT. By moving away from the depletion region edges, the concentration of the minority charge carriers on both sides exponentially reduces. Let me ask you something, but before asking my question, I want you to first focus on the N semiconductor. Near the depletion region edge, we have lots of holes and they are hungry for electrons. At the same time, in the N semiconductor, we have lots of free electrons because they are the majority charge carriers. So what do you think will happen? Think about it for a few seconds. What happens is that free electrons in the N-type semiconductor recombine with the diffused holes. At first, you might think as a result of this recombination, I have now less free electrons on the N side. But it is just not correct. What you need to pay attention to is the metallic contact connected to the right end of the N semiconductor. This plate has electrical connection to the negative terminal of Vd, and it has lots of free electrons. And once the recombination happens, new free electrons enter the N semiconductor. At the same time, holes are still diffusing into the N semiconductor, and therefore the process that I just talked about continues. Now, let's focus on the P semiconductor. Due to the electric field of the external voltage source, free electrons are repelled from the negative metallic contact on the N side, and they are encouraged to diffuse into the P semiconductor. As a result, the concentration of free electrons near the edge of the depletion region significantly increases. By moving away from the boundary of the depletion region, the concentration of free electrons reduces exponentially. Once the free electrons diffuse and arrive at the P semiconductor, they recombine with the majority charge carriers, holes, in the P semiconductor. However, due to the thermal excitation, generation happens, and due to the external electrical field of the positive metallic contact, electrons move toward left and they are finally absorbed by the positive metallic contact. The free electrons are now in the conductive wire. They go to the voltage source, and from the other side, they enter the device. I hope by now you have come to this realization that how the current flows in this closed loop circuit when the diode or the PN junction forwardly biased. As long as Vd is larger than 0 and smaller than the built-in voltage VBI, the current flow is not significant. However, when Vd is equal VBI, the resistance of the depletion region becomes so small and in fact becomes negligible. Therefore, the current can flow through the device almost without any hindering process. Please note that the neutral regions of the N and P type semiconductors have some electrical resistance, but as far as I'm concerned in this lecture, we can assume that resistance in the neutral regions is 0. Here is a simple drawing of a PN junction which is forwardly biased. As we have seen so far, the current flow through the device is due to the charge carriers, holes, and electrons. This is why we categorize the PN junction diode as a bipolar device. I plotted the minority charge carrier concentrations for a forward biased PN junction, and now it's the time to plot the current density diagrams across the device length. The yellow diagram is the current density due to the holes, and the green diagram is the current density due to the free electrons. What these curves show is that close to the metallic contacts, the majority charge carriers are responsible for conduction, and as we get closer to the depletion region, the minority charge carriers. In the depletion region, Jn and Jp become flat. This means that in the depletion region, no generation and recombination processes take place, and the hole and electrons just pass through the depletion region. Adding Jn and Jp gives us the device total current density, which I called J. Since Jn and Jp are complementary, J becomes a flat line. In this lecture, I discussed the effect of the forward biasing on the depletion region with concentration of minority charge carriers under forward biasing and the current flow mechanism under the forward biasing. In the next lecture, I will explain the reverse biasing of the PN junction. Thanks for joining this lecture of Peacademia.